Melanie Fernandez Pradier from Microsoft Research, and she is going to talk about From the Research to the Clinic, aligning ML systems with clinicians for improved mental care. So Melanie, when you're ready, share your screen.
All right, thank you for having me today, and also congratulations everyone for making it to the last invited talk of this conference. Also, I appreciate for letting me join remotely. So today I'm going to talk about some of the works that my colleagues at Harvard and I did just before I joined Microsoft Research. I will share my experience working on interpretable machine learning models for personalized mental care. And please feel free to jump in and ask any clarifying questions during the talk. Otherwise, we will have the short Q&A at the end of the presentation as usual. So please let me know if there is any question in the room. All right, so before I start, I would like to raise attention to the noticeable gap that exists between machine learning research in scientific publications and the real world. So although machine learning has flourished in the last decades, revolutionizing fields like computer vision, natural language processing, and speech processing, success stories deploying machine learning systems in the clinic remain limited in comparison. So in the context of healthcare, machine learning systems often achieve high performance in research papers, matching or even exceeding human clinicians. So then why are we struggling to bring such promising machine learning research to the clinic? And obviously there are barriers at several levels, logistics, engineering, administrative considerations. But if we focus on research aspects solely, here in this talk, I argue that lack of interpretability and misalignment with clinicians are frequent red flags when deploying such systems in the clinic. So in this talk, I will share my experience trying to bridge the gap and trying to bring machine learning research to the clinic in the context of mental care. So in the first part of the talk, I'll give a brief introduction on AI for mental care, why it matters, and what kind of problems machine learning systems are able to solve. So leveraging information from electronic health records. So after some success stories, I will also share some unexpected negative results that we got via user studies. And so a word of caution, basically, and that is that a combination of human plus ML system may actually underperform compared to the clinician alone. So we have to be careful when we deploy those systems, right? But still, there is potential for machine learning to be helpful in such domains. And so in the second part of the talk, here, point 3, I'm going to present an approach that seeks to increase alignment of machine learning systems with humans as much as possible. And so increasing overall performance of human plus ML systems in combination. All right, so mental care is a very pressing problem in society. I don't think I have to convince you of that, but just to give you a few data points. So according to the World Health Organization, 1 in every 8 people in the planet live with a mental disorder. Then depression is a leading cause of disability worldwide. And suicide is the 4th cause of death in the population between 15 and 29 years old. So there is this pressing problem. And now with this digitalization of health records, there are several opportunities for machine learning research to improve mental care. So a few years ago, my colleagues and I started looking at the problem of personalizing antidepressant prescriptions based on electronic health records. So the key question that we ask is, given those electronic health records, can we train machine learning systems to give valuable insights that help clinicians prescribe better antidepressants? So there are three important aspects to consider when prescribing antidepressants, here depicted in this triangle. These are efficacy, tolerability, and safety. So efficacy concerns or refers to whether the drug works, right? So does the drug has an effect or not on the well-being of the patient? Then tolerability refers to how much side effects the drug in question causes. And those might be unrelated to the mental disorder, actually. It could be, side effect of insomnia, irritability, overweight, etc. So the last aspect, safety, refers to how likely a drug is to worsen the mental state of a patient. So for example, you want to be especially conservative with patients at higher risk of suicide. So in our work, we look at electronic health records to define computable proxies for each of these three aspects: efficacy, tolerability, and safety, and use machine learning systems to predict such proxies. So here are some of the works that my colleagues and I basically work on. So we look at three prediction tasks given the billing codes in electronic health records. First, can we predict treatment stability? And that's defined as, will a patient stay on the same combination of antidepressants for a long enough period of time? Because that would indicate if you are having a same antidepressant for a few years, probably it's actually helping, otherwise you will stop. Yeah. The second prediction task was, can we predict whether a patient will drop out earlier than advised medically? And the truth is that actually around two-thirds of the patients will discontinue their treatment earlier than they should. So that's a very important problem in psychiatry. And the third problem that we look at was, can we identify early on when a patient with major depressive disorder will transition to bipolar disorder? So this is a common misdiagnosis that can actually cause a lot of pain to patients, when not treated accordingly. So okay, so for all these predictive tasks, we use different models. I'm not going into many details, but basically models like logistic regression, random forest. We use topic models. And yeah, so the summary is that yes, it was possible in those works to use machine learning systems to make such predictions and actually improve above baselines that have value at the moment for clinicians. So we were reaching AUCs in the order of 60s or 70s, which, it's not great, but still it's promising. I mean, it's a very complex type of data. And again, we have to make sure that we are comparing against the right baselines. So it's still promising against those and with the potential to make a difference or an improvement in the clinic. Yeah, for example, as a final example, in the last paper of bipolar disorder, so we had a held out center. All of these, we actually trained, we had access to two data sets of two separate hospitals. And we always train on one, validated externally on the second one. And so we were able to consistently detect patients with 3 times higher risk of transitioning to bipolar disorder after having a diagnosis of major depressive disorder. All right, so that's great. And we were very excited when with these results, but still the endpoints that we were predicting were just proxies for what we actually cared for. And then it is still unclear how much would such machine learning systems actually help in reality, right? So what would the real impact be? And for that, we actually went into the road of actually conducting user studies, and with the goal of understanding how clinicians' treatment decisions are influenced by these machine learning recommendations and explanations. So we conducted this within subject factorial user study, and we queried 220 clinicians. We showed them a set of patient vignettes, and we collected some ground truth from 5 psychopharmacology experts, which, based on those descriptions of the vignettes, I'm going to show you an example in a second. Based on the description of a situation, patient A comes at the clinic, it has this and these properties. Which antidepressant would you actually recommend? And so our experts would actually rank all the options available, and we will compute the ground truth based on the average of those. Also making sure that we focus on the top ones and the highly top ranked, and for the right, so for the correct recommendations. And then we, as I'm going to say in a minute, we also show them incorrect recommendations. So here, because here the goal was to see, okay, how would actual recommendations plus explanations influence clinicians? So the variables that we were changing in the user study were recommendation could take values as none, there could be correct recommendation or incorrect, and explanations could be either inexistent, placebo, which would be something like this recommendation was based on electronic health records. That's it, just a sentence. Feature-based would be some sort of visualization of top rank features, and rule-based would be a more complicated description of, okay, we are giving this drug because it's safer, or because it doesn't cause insomnia, etc. Something like that. All right, so we evaluated the impact of the machine learning system by looking at treatment selection accuracy based on concordance with respect to this expert psychopharmacologist ground truth data. So here's one example of such user study. And here the recommendation will look like this, a list of scored, ranked, so antidepressants ranked by the score of our machine learning system, and on the bottom, optionally an explanation. And okay, the takeaways were actually quite surprising to us. No? So the first one is that we found out that correct recommendation actually were not helping. All right, but most strikingly, incorrect machine learning recommendations were actually hurting. That is, explanations were not enough for addressing our reliance on imperfect or incorrect recommendations of the machine learning algorithms. One important aspect is that, so in the explanations, we have feature-based and rule-based, and we noticed that feature-based explanations would actually tend to lead to worse, to a bigger degradation in accuracy, as opposed to rule-based explanations. And so one hypothesis that we have is that it could be because the rule-based explanation actually, so it's going to interact more, or it's going to get the clinician also involved in the decision, whereas a feature-based explanation is a simpler rule, and it just is easier for the human to actually just follow the incorrect recommendation. All right, so at this point, we were a little bit like without much, at a loss of, okay, how should we proceed, right? So we have machine learning systems in the publications that actually we have seen they can perform pretty well. And yet, in reality, when we test that with users, with true real clinicians, we see there is a risk, and we see that there is actually a mismatch. So further conversation with clinicians highlighted the importance of alignment between humans and machine learning systems, which is the origin or the reason why we went to develop a model that actually is trying to learn to assist, okay, trying to adapt to the human. Okay, and as final takeaways is, so again, I think that interpretability and human alignment of machine learning systems with humans are crucial if we really want to bring the research to the clinic. We need to not only think about the model, but think about how and when those systems will be applied. And then very importantly, we need to talk with clinicians to optimize for the right properties in your machine learning models and for the right downstream tasks. Okay, and obviously, I would like to thank my wonderful collaborators at Harvard and from both the computer science, also the human-computer interaction, as well as the expert, so our collaborators, expert clinicians at the Massachusetts General Hospital. Thanks again for listening, and I'll be very happy to take any question from the audience.